We will start the study of the generative models, so we can think of them as a way to sample from complex distributions that are never explicitly stated. So let's say that we have a complex distribution such as this one, and we want to sample from it. So we take a random distribution from which we know how to sample, and then so we take just any number, go through the generative function, and then the generative function produces an output as if it has been taken from this distribution. Here is a high dimensional example. So let's think of the distribution of all the possible images taken with a camera in the world. So that distribution is never explicitly stated. So we take a random sample from a multivariate Gaussian. We go through the generative function, and then the generative will produce an output that is synthetic because it is a transformed version of this one, but this synthetic comes from the distribution of all possible images in the world. So a possible architecture to do that is these generative adversarial networks. So the generative adversarial networks, it has a generator network and a discriminator network. So the generator network takes the random noise and transforms it into a sample that the discriminator will try to determine whether it is fake or it is real. So real is 1, fake is 0. So from the discriminator point of view, this is the function that it would like to minimize. So when the samples are coming from the true distribution, so they produce 1, and so we are encouraging the discriminator to say 1 here, while if it is coming from a generated image, we should encourage to say 0. So this is so the discriminator is trying to maximize this function. However, from the point of view of the generator, what it is trying is to minimize the loss function here. So actually this is not a loss, this is a kind of gain. The higher the better. So the discriminator is trying to maximize this thing, while the generator is trying to minimize the successes of the discriminator. Here we have some examples of numbers generated by this generator from random noise. The discriminator has to say whether these numbers are really coming from a person or they are artificially generated. We have seen already variational autoencoders. So the variational autoencoder, you start with an image, and then you embed it into some latent space, and this latent space representation is used to recover something that looks like the original one, and there is some randomness here. We have seen the GAN. So the GAN, the generative adversarial network. It is called adversarial because the generator and the discriminator are trying to fulfill opposite goals. So this is just the GAN that we have seen. So we have GANs. So it is an architecture that is a mixture of the two. So here on one side we have an image, and it is trying to produce something that is that looks like the input image, and then this one is generating some random fake image that goes through the generator, and the generator, so the discriminator has to distinguish between this part and this image and this image, or even this one. So the thing is that this generator is helped by having this autoencoder here. Then we can have conditional GANs. So conditional GANs, this is the standard GAN. In the conditional GAN, we have also labels. So for instance, let's think of the digits. So we have the image that is X, but we also know the label associated to that image. So this is 2, this is 7, this is 1. So we can help the generator to generate a 1. So we say, okay, now you are generating ones, we'll take random noise, generate a 1. Or now you're generating 4s, now this is 4, you take random noise, generate a 4. And now the discriminator has to distinguish, knowing what is the label of this generated data. So whether it is a true one or a fake one or a synthetic one. We can have adversarial autoencoders. So the adversarial autoencoder, somehow we have the standard autoencoder here, and then the latent space representation is input to the discriminator. So this is the discriminator. This is not a true subtraction. So this is just a way to represent that sometimes it is getting samples from random distribution, or sometimes it is getting samples from a true encoded true image. So here the adversarial cost is to distinguish whether the sample, the distribution here, so it is at the level of distribution, whether the distribution here coming from this branch is a distribution coming from true images, or it is a distribution coming from this one. And here we have some results for the adversarial autoencoder, comparing it to the variational autoencoder. So it seems that can achieve better separation of the digits, for instance. And we can combine this with supervision, so we can generate, for instance, here in the autoencoder, we can help with the true label, so the decoder part knows that this is a 1, and then it has to generate a 1. We can have a semi-supervised autoencoder in which all this part stays the same. Now the prediction, so this y that we had before, this y is coming from the encoder part of the autoencoder. So now there is another discriminator. This discriminator for a batch has to say whether the set of y's that are coming from the batch is coming from the autoencoder, or it's coming from the encoder of the autoencoder, or it is coming from truly generated labels coming from the data set. So this somehow encourages that the distribution of y's produced by this autoencoder, the proportion of y's is similar in the generated data and in the true data. Another possibility for autoencoders is to have masks. So here we take patches of the image, and so we are masking implicitly many other regions of the image. So the patches go through an encoder, and then this encoder, so this encoded data is somehow filled in following the same structure as the input data, as the input grid, but with missing values here. And then the decoder has to take all this input and produce an output that somehow resembles the input image. And here you have an example. So given these patches, this ground truth, this one is this network is producing this thing. This is called masked autoencoders.